Hi there, Himanshu this side, and I'm the physics faculty at askIITians. So welcome to the new chapter sound. And that's our lecture number 1 for the chapter sound. I hope this lecture you're studying for the first time in the grade 6, 7. The chapter sound must have come for you, but that was a very simple introduction. I guess you have heard of the term called waves, then a pitch. These kind of terms you must have done in the lower grades only already. But here in the chapter in the grade 8, you will be getting to know different types of wave, of course, and then what is sound wave exactly, right? And how do we hear a sound? Okay, so that's a major discussion we'll be having in the 3 lectures of the sound chapter. Okay. So let us begin now with our lecture number 1. So lecture number 1 is mainly talking about the introduction and then the oscillations and vibrations. What do they mean exactly? And then what is wave motion? And in the end, we'll talk about the types of wave motion. Okay. So first of all, let us do an activity before we start. Okay. So the activity is what we have to do here exactly. You put your finger on the neck and say ah. Just say ah, right? Now, first of all, you try to say as loud as you can. Oh, right. So that was like when you say ah, that time I could feel some vibrations here, right? Even you try to speak vibration, right? So when you try to speak vibration, you can feel that something is vibrating over here. Similarly, uh, now next time you do one thing, now you try to say ah slowly. Ah, I don't feel that much vibrations now. But when I say it louder, now I feel ah. So that's a difference. Like, so basically what do we get to know from here? That when I said loudly, ah, I could feel the more number of vibrations. And when I say uh, it softly, I was not able to feel there's that many number of vibrations. So now look at this guy, how loudly he's saying, right? He didn't follow our second statement that he had to say soft also. All right. So he's just saying loudly. And he didn't even put his fingers. So his intention was just to say loud ah. He was not interested in knowing whether it is vibrating or not. Okay, anyways, going ahead. So basically, why did we do this activity? The purpose of doing this activity is so that you can understand that sound is an important thing. Vibration is an important thing to produce sound. So when vibration occurs, something when vibrates, it produces a sound. Yes, exactly. So that's the basic idea we will get from here. Okay. So any sound production, any sound source you take, it must be vibrating something. So when it vibrates something, then only we get a sound wave. I hope we you have got my idea that what I'm trying to say. So for production of sound, the vibrations are important. Okay. Now what exactly happens when a sound wave when a sound travels? All right. So let us understand the sound in bit more detail now. Okay. So what is sound? So do not get confused with the wave part right now. I will be having a discussion with you guys about the wave in detail just after 10 minutes. So right now, let me just talk about the sound and the propagation of sound. Okay. So let's see what happens exactly. This thing you can see, what is this? And if anybody knows, it is called the tuning fork. Tuning. Oh, so just a second. It is called the tuning fork. So it's basically made up of a metal, and you will find this thing in the labs. So in the grade 11, 12 student do these experiments with the organ pipes. Okay, so you would also be doing it when you'll be entering in the grade 11. But for that, you need to take science. No worries. Even though you don't take science, still you can uh, purchase this tuning fork, and you can do the different experiments in the resonance tube as well. Okay, so you can also try this. So what is this tuning fork basically? It is a device on this every tuning fork you will find that the frequency is written over it. 512 hertz, 502 hertz. Okay, so when you beat the tuning fork with a hammer, so what will happen? It will start vibrating. Its prongs will start vibrating. Though it's a very metal, so you won't be able to see it, whether these prongs are vibrating like this or not. All right, but the vibrations are happening there, and that's why it is producing a very sharp sound of a certain frequency. Okay, and that frequency is mentioned over every tuning fork. So you can see here this tuning fork is vibrating. Okay, so now when this tuning fork is vibrating, what it does basically, right? So let us try to understand this thing here. Yeah, from this way. So this is the sound source. The sound is being produced from this place, and this is ear. So sound has ultimately to go from the source to the ear. So source is placed there, and listener is on the other side. Okay. Now, actually, what happens? Let us take one example, and then we'll understand all these examples, all these pictures which you are able to see on the screen. So suppose you have one container. Just a second. Yeah, let's take one container, and in that container we have gases. So these are the gases inside the container. Okay, or you can say simply some air particles are there. Some medium is there. Okay, all right. And this side on the one end, let me put a piston over here. So that is the piston. Okay, it's a movable piston. So you have the handle. So with the help of this handle, you can move the piston forward. You can bring it backwards, and forward you can bring it backwards. Okay. So let us do one thing. Let us move the piston. So actually, what will happen? I'm moving the system forward. Sorry, piston forward. So when you move the piston forward, what will happen? These gases will get compressed. You're moving the piston forward. So actually, what will happen? These gases will be compressed. Okay. So the piston will reach somewhere here. So when this piston will reach here, that's the new location of the piston. Let us call it A. Okay. So originally it was at O. So you have compressed the gases now because you're pressing it. So when you're pressing it, the gases will get compressed. Okay. And now you bring it back. So from O to A, it was a compression. And now you are bringing it back. So from O to A, compression. Now you are bringing it back. Still the gases are compressed. When you're bringing it back from A to O, still the gases are compressed. Now you take it backwards. Backward means beyond O, on the left side. So basically from O to A, you compress the gases. And now when you pull it outside, means O to B, now what you're doing, you are taking out some gases with you. See, when you will pull it like this, originally what you were doing, this was the original situation. Try to imagine. Suppose that's a piston, and that's the original situation right now. So I'm pressing it. Okay, so this was the original situation, this end, and now I have pressed the gases. Now I'm bringing them back. Okay, so still till this situation, this was a normal situation, guys. So even though you press the piston and you bring it back, till this situation the gases were compressed only, right? And now when you pull it back, so what will happen? It will try to take out some gases along with it. Okay, so now you are expanding the gases from here to here, compression. And now when you take it outwards, it's expansion of gases this way. So similarly, I'm saying here, when you go like this and when you bring it back like this, it is called the rarefaction. It is called the rarefaction. Rarefaction means the pressure decreases. The pressure decreases. Compression means the pressure increases. On what? On the medium particles. So compression means the pressure increases. Rarefaction means the pressure decreases. So compression means going this way and then coming this way. Rarefaction means going outwards and coming back. So in this way, what will happen if you look at the particles motion, they will vibrate like this, right? So they'll go back, they'll come back, they'll go like this, they'll come back. That's called the compression rarefaction. So compression, then rarefaction, right? That's a nice presentation, I guess. Okay, so you go this way, compression, you come back, and then you go this way, then you come back. So that is the rarefaction. All right, so when I go this way, it's a compression. So I'm compressing the gases. So pressure will increase now, right? Okay, so volume will decrease now. Got my point? So density will increase now. Don't get confused if I'm going too high, right? Simply understand that pressure will increase, so volume will decrease, right? It will compress the gases. It will bring the gases closer. So volume will decrease. Now density is inverse to the volume, so density will increase. So when I'm pressing this, it is going this way. So volume decreases, density increasing. So pressure is also increasing. When I'm going this way, the volume is expanding, right? So when volume is expanding, the density is decreasing. And pressure is of course decreasing because gases are going far away now. Okay. So rarefaction means low pressure. Compression means more pressure. Am I clear? So that's how exactly the sound also does. So when we speak something, what we do, we are producing the compression and rarefactions. Right. Now, when we speak, we are producing the compression and rarefaction. Compression and rarefaction. So these medium particles, like suppose if I'm speaking here right now while teaching you, then if person is standing there, if one person is standing there, if one person is standing there. So now these compression rarefaction will travel to everyone. I am not going there. I'm not going there. I'm not going there. My compression and rarefaction, which I have produced here, right? Which the pressure which I have produced here, I was acting like a piston now in this situation. So that piston has pressed these air molecules. So these air molecules will travel. These air molecules will, oh sorry, they will vibrate. These air molecules will vibrate. These air molecules will vibrate. So wherever you have the air molecules, they all will vibrate. And that's why the sound goes in all possible direction. It's not like sound will go in a single direction. Anywhere, like if it's an entire class, the all 40-50 people who are sitting in the class would be able to hear me. So basically the thing is like when I'm speaking, then I am pressing the particles. So that is producing a compression rarefaction like this. Okay. So every particle will stand on its own position. It will not go from here to there. If you talk about these particles, then this particle, what it is doing, it is going this, it is coming back, it is going this, it is coming back. As you move the piston, it goes forward, comes back, goes this way, comes back, right? So actually every particle is oscillating. That's called an oscillation, vibration, right? Very fast movement about its own position. It is going forward, coming back, backward, coming back. All right. So basically that is called the oscillation, right? To and fro motion. It is also called the to and fro motion, right? We'll talk about it just after 2 minutes. So that's how the sound is basically traveling, right? So we are basically producing compression rarefactions in the medium, and that compression rarefaction is traveling forward. If you look at one particle, then what this one particle is doing, it is just going forward, back, back, come back, going forward, then coming back here to the original position, then going this way, and then coming back to the original position. So everyone is dancing at their own position like this, right? That's it. So that's the production of sound. Everyone is dancing at their own position. So this guy makes to dance the another guy will make the dance for the next person. In this way, everyone is making the like it's like a reaction. So you have made the first particle to dance this way, then this particle will make the second particle to dance, second will make third to dance, third will make fourth to dance, fourth will make fifth dance, but first will not go to fourth. So every particle will oscillate or vibrate at their own position. Got my point? So that is what we call the propagation of sound. Yes, all of you? Okay. So basically that's what we call the propagation of sound, right? So that's how the sound travels. Now here we can see that's a speaker. It will produce compression rarefaction. So you look at this guy. Let me track the motion of this guy. So this guy goes forward, it comes back. Just look at this. Yeah, it's going forward, it's coming back. Let us try to look at this. Yeah, let us try to look at this one. Yes, so they all are going forward, they all are coming back. Yeah, exactly. So, but from where it all started? It started from here. That was a source. And these are your ears. So finally the sound will reach at the ear side, and then in the ear we have the eardrum that will vibrate, and then I don't know, it's a biology section, right? And then the entire biology is taking place, right? You're able to detect those sound waves and all. So that's a different story. Maybe we'll have a little bit idea about it at the end of the chapter, right? About the ear structure. So that's how basically the sound travels from source to the end. Yeah, you got my point. So that is what we call the propagation of sound. Perfect. Okay. Now coming back. So from where did we start? Here, what was vibrating? The tuning fork was vibrating. It was producing a sound. So medium particles are vibrating at their own position, right? So the back and forth motion or to and fro motion, right? Not frog, it's a fro. Okay. So particle is going back forward, then coming back. So first particle goes from here to there, 1 to 2, then comes back from 2 to 1, and then goes from 1 to 3, and then comes back from 3 to 1. All right. So 1 to 2, 2 to 1, 1 to 3, 3 to 1. So all these things are like a dance steps. 1, 2, 2, 1, 1, 3, 3, 1. Right. Then again 1, 2, 2, 1, 1, 3, 3, 1. Right. So the particles will dance, will follow this step. 1, 2, 2, 1, 1, 3, 3, 1. Every particle will dance at their own position. You are not allowed to dance from your location to that location. You have to make other people to dance also. Right. So that's what we call the definition, the back and forth motion. To and fro motion also you can call. And that is what we define as the oscillation. And when these oscillations are very fast, it's called the vibrations. Right. So basically that's what the meaning of, that's how the sound wave exactly travel. So sound is produced when something vibrates. The vibrating body causes the medium, right, to vibrate. Like suppose it can be an air, it can be a solid particle, it can be a liquid particle, it can make anything to vibrate. Yeah. So here you can see, like when we play this drum, dum dum, so that membrane is vibrating. When this membrane will vibrate, sound will be produced here. All right. So that's basically what we call the production of sound, and that's how the sound is basically traveling. Okay. All right. Now the thing is the another part, the production of sound, right? That's what we have discussed, and then the propagation of sound. So that's how the sound wave is basically traveling, right? Now let us begin with the wave motion. Okay. Yeah. Now what is the wave motion? I'll come back to sound part again. Don't worry. Right. I'll again relate whatever we have discussed so far. I'll be relating with the wave motion, but let us make some terminologies clear first of all. Then it will be easy for all of us to do this. Okay. Yeah, let's begin. Okay. So first of all, guys, in the wave motion, what is the wave motion basically, and what does it refers to? So right now you forget this term wave motion. We'll talk about it. Right. What something is related to the motion here. Something will be in the motion, of course. And what is that something in the motion? That's what let me discuss with you guys. It's a very beautiful concept which you are learning it for the first time. Suppose we have few people standing in the queue. Person 1, then here we have the person 2, person 3, 4, 5. I guess enough. Yeah, so 5 people are standing there. Okay, so let's say we have some parcel for the person 1 and we have to give it to person 5. Now one way is like person 1 will walk and go to person 5, right? But another way is he will pass on to person 2, 2 will pass on to 3, 3 will give it to 4, and the person number 4 will pass on this to person number 5. That is also one of the option, right? So if you look at this particular type of motion, this one, when 1 was passing to 2, 2 was passing to 3, 3 was passing to 4, and 4 was finally passing to 5. Now in this particular type of motion, you must have observed something that this particular motion, 1 to 2, 2 to 3, 3 to 4, 4 to 5, here basically we had no person was shifting from their own location. They all were standing here only. The person 1 was standing there, person 2 was standing there, person 3 was standing there, person 4 was standing there, person 5 was standing there. Everybody was standing at their own position. Yeah, exactly. So everybody was standing at their own position, and still we have made this work get done, right? So parcel was got ultimately transferred from one place to the fifth place without even movement of the person 1 from its location to the person 5 location. Okay, so that is what is the wave motion. So what is the wave motion? So wave motion is basically the transfer of energy from one point to another point without actual transport of matter between 2 points. It's too technical. Let us just apply this here in this diagram. See, all these, it's a water container or water pond you can take. I am disturbing this end of the water. Okay, I am putting the water from top. So basically this end of the water is getting disturbed. This red mark. Now this thing should not get disturbed. This thing should not get disturbed. This thing should not get disturbed because I am putting the water at this level. So why everything else is getting disturbed? So basically what happens when you exert some force here, which I am referring as a disturbance, right? Or you can call it a passing of energy. So basically that is the passing of energy. So I'm producing some disturbance at this place. All right. Now this disturbance will go forward. Every direction. In every direction, this disturbance will travel. Okay. So in every direction, this disturbance will travel. Right. So first will make second to disturb, second will disturb third one, third will disturb fourth one, fifth, sixth, seventh, eighth, ninth. In this way, all these particles will be getting disturbed, actually. Are you getting my point? So that is what we call the wave motion. So basically, you have transferred your energy to this place, but that energy got transmitted from this place to the end place also. So did this particle move there? No, this particle didn't move. Still the energy got traveled, right? So that's what we call the wave motion. Here also you can see this is a Tesla, right? So Tesla is going from one place to another place. It is producing a sound, right? So when horn is being produced, so sound will be traveling from here. So this sound will be going in all possible directions, right? So it's not like if the person is standing here, he'll not get the sound because the sound was produced at this place. No, right? So basically the sound has been produced at that place, but due to the medium particles, the sound will be traveling this way also, this way also, this way also. So actually the medium particles will remain at their own position. They will vibrate at their own position and they'll make the other things to vibrate, their neighbors to vibrate. So everyone is interested in disturbing their neighbors. I think you like that, right? And you are good at that. No? So basically our main goal is to disturb the neighbors here for the propagation of wave motion, right? Okay, so that's what we call the wave motion, transfer of energy from one point to another point without actual transport of the matter. Okay, now let us understand there are two types sorry, there are two types of transverse wave, right? So first of all, it is a there are two types of wave motion. So first one is a transverse wave motion. Now I don't know whether you have heard this term from biology or not. Transverse means perpendicular to the length. Do you know this? This is the length. Transverse means 90-degree to it. Transversal cut, 90-degree cut. When you get the tangential cut, this is transverse cut. When you get the tangential cut, it's longitudinal along the length. So on this basis, we have two types of wave, longitudinal and transversal. So what is transverse? When vibrations are happening perpendicular to the directions of wave energy propagation. Very simple. See, suppose if I am standing here at this place, this is me, and I have the string in my hand like this. Imagine like this guy in the picture number 2, the bottom one. This guy is having a string. Other end of the string is tied to a wall. So that is fixed. Now what I'm doing with this string, I am producing a wave. I am just vibrating this end, only the first place. I'm not doing anything with that. I am just vibrating this at my end like this. So when I'm vibrating my hand like this, the string, the entire string, the wave will move like this. Right? Okay. So you look at the motion of any particle. Let's look at this guy. I'm not able to track him. Let us just look at this guy. This guy is going up, coming down, going up, coming down. Right? So particle is not going forward. Particle is vibrating at their own position. Right? Up, down, up, down. Any particle you can pick. Suppose if somebody picks this particle, it's going up, it's going down. Again, it will go up, it will go down. So that's what we call the transverse wave propagation. Now read the statement. Particle vibrations perpendicular to the energy propagation. So at wave was ultimately going forward. I was vibrating my hand like this, the wave was going forward. But how the particles were vibrating? Up, down. So particles vibration like this and wave movement like this. You can see one more example here. It will be producing disturbance at this place. See, just a second. Yeah. See, this has been produced here. See, the wave is going forward and every particle is dancing. You can observe this black color box. See how it will dance as the wave will come there. Wave going forward, particles dancing up, down. So this black color box didn't go forward. All right. So that is what we call the transverse wave propagation, in which the particles are vibrating perpendicular to the direction of propagation. That's it. Okay. Let's go forward now with the longitudinal waves. So here comes the longitudinal waves, right? Which is basically the sound wave. So transverse wave, wave on a string. It's a transverse wave. I can give you one more example, though you would not understand much about it. It's called the light wave. Now light is an electromagnetic wave. Electromagnetic wave. So that is also a transverse wave. Their electric and magnetic fields are vibrating. Electric and magnetic fields are vibrating. All right. So that is what we call the light wave. That is also an example of transverse wave. Okay. Let's go forward with the longitudinal waves now. What happens in the longitudinal waves? So here the particle vibrations in the longitudinal waves are not perpendicular to the wave propagation. They are in the direction of wave propagation. We have discussed this in very much detail now. Sound is going forward. Right. So basically sound will be going forward. But when you look at the motion of these particles, so if you look at here, then these particles will go forward, they'll come back. Very carefully you have to see them. Let us look at this particle. It seems like they are going forward, but they are not. Just a second. Yeah. Very carefully you try to see them. Spend 2 minutes over there. Just try to focus yourself at a point. You'll find that particles are going backward, forward, backward, forward, backward. As the piston moves, it comes back. So that's what we call the compression rarefaction. So compression, then rarefaction. Compression, and then again rarefaction. That's how basically the sound waves are being moved. Sound waves are nothing but the longitudinal waves. When the particles are, vibrations are happening parallel to the wave propagation, right? So that's what we call the sound wave. All right. Okay. So that's all about the longitudinal waves. Okay. When the particle motion is parallel to the wave propagation. So here you can see that's a spring. You make the spring to vibrate like this. So all the rings here will vibrate this way. And energy is also going forward. That disturbance is traveling forward. That's what we call the longitudinal waves. So that's all, right? So that was a quick introduction, a very small introduction about the sound wave. Okay. And we have discussed about what is a sound wave, how does it propagate basically. So vibrations are important. And then it makes the things to vibrate. And when you make the things to vibrate, then the sound propagates basically. All right. And then later on, after that, we discuss the types of wave motion. So in a wave motion, the matter do not leave their position, they vibrate at their own position, right? But they will make the other things to vibrate at their own positions, and that's how the entire disturbance will be traveling forward. Then we discussed about the transverse wave. Particles are vibrating perpendicular to the energy propagation. Longitudinal waves, particle vibrations are parallel to the energy propagation. So that's all, right? So I hope you enjoyed the lecture, and that's all from my side. Okay. And if you want to know some other questions, if you have any other doubt, if you have any other info, just put it over the PDF. You'll get all the answers there, right? Okay, then thank you so much, guys. Bye bye. Enjoy. All the best.